Hello everyone, welcome back to STAT385 for another video. In this video we're going to go over the second lab, writing R functions with vectors. Hooray. Alright, so we have, don't forget to read the lab policy again, and this would be the second lab for credit. Okay, so let's get started. Alright. Okay, so I have my RStudio ready to go. I'm going to keyboard shortcut, create a new script. I'm organized here. Oh, I need to create a new folder. Folder. Okay. Lab 02. Oops. Delete. Yes, go back. Sorry. Folder lab 02. Okay, good to go. Okay, so now, all right, so I have, I'm in my STAT385 project, create a new folder, and I'm going to save this in that new folder, lab 2. Okay. All right, so what do we need to do? All right, so we need to create 3 vectors in R, assign them the names foo, bar, baz, those sort of throwaway variable names that we talked about. Okay, I'm going a little bit fast. Let's see what we need here. So foo should store integers between -10 and 10. So I'm sure that there's multiple ways to do this, but the first one that comes to mind for me is this right here, -10:10, and let's see if that works. That looks right. Let's verify that these are in fact integers. Okay, good. Okay. All right, sounds good. I'm just gonna work under here. Okay, so bar should store 0 and then all multiples of 5 until and including 100. Okay, 2 ways to do it. Well, I'm sure there's many ways to do it. There's 2 ways that come to mind for me, and of course, we're not going to try to type out all of these values. So first is exploiting a little bit of length coercion. So 0 to 20 times 5. You see it? Okay, let's run it. So essentially I'm running all the integers from 0 to 20, 0, 1, 2, 3, 4, and then multiplying each of them by 5, exploiting length coercion. Okay, so that definitely works, and that's a very quick way of doing it. Let's do a way that's a little bit more transparent. The sequence function, which we definitely talked about during lecture. 0 to 100 by equals 5, and that should support okay. So they're the same. Awesome. And then baz should store the letters A, B, and C in that order repeated 10 times. 1 letter per element of the vector. Okay. So A, B, C. And I'm not going to copy and paste this 10 times. Instead, we can use the rep function time, oops, wait, what? Okay. A, B, and C in that order repeated 10 times. A, B, C, A, B, C. Okay, looks good. All right, awesome. So additionally, create 3 more vectors. Assign them the names power of foo, mean of bar, and count of baz, respectively. Okay, so powers of foo equals, and this should store 10 raised to the powers of each value in foo. Okay, I'm getting ahead of myself. Okay, sorry. 10 raised to foo. Let's see what it does. Okay, looks about right. Do we have, we have 0 in there. Okay, yeah, looks good. And then mean of bar. And count of baz. And our studio is complaining because I have an equal sign here. Nothing assigns to it. Okay. So let's see. So mean in bar should store the sample mean of the values in bar. Easy. Okay. And then baz is a little, okay, so count of baz should be a vector of length 3, which stores the number of times each of the letters in baz appears. And I have this hint, use the table function. So, all right. So you can, read this in your own time. But basically, what this is going to do is it's going to create a named vector that counts all of the unique elements or all the occurrences of a unique value in a vector. So that's going to be very handy here because you can see that it has the counts of each of the elements A, B, and C. All right, so awesome. And that is a vector of length 3, which stores the number of times each of the letters in baz appear. Okay, awesome. So that is good to go. Okay. So, did I put this in the right place? Okay. I'm just gonna pull up STAT385, lab 2, vectors. Okay, save and grade. Assessment overview. Okay, so it says I got it right. This is really okay. Prairie Learn's a little bit slow for me. Okay, so let me bring back our studio. All right, so then let's go to counts and proportions. All right, so let's new thing. File save. Counts. Right? Yeah, counts.r. Okay. So what I want to do is write okay, so there's a few functions that I want to create. A function count and prop grader equals function, and that takes 2 arguments, x and c. Okay, so one little convention that we're going to adopt in this lab, and something that I really encourage. I know that sometimes when functions are simple, you won't do this. You'll just enter text right into the body, but it's good to get in the habit of writing code for a function outside of the body of the function so that you can test it as you go. And then when you're reasonably confident in that code doing the correct thing, then you can put it in the body and then try the function again. Just a little bit of debugging or a little bit of good practice up front that will make potential debugging a lot faster. Okay, so x is a numeric vector and c is a cutoff value, and the function should return a named vector with elements count, which is the number of values in x that are greater than the cutoff values c, and then prop the proportion of values in x that are greater than c. Okay, so if I were to have assigned this as a quiz, you might get mad at me because we haven't fully talked about this in the lecture, although we will next week, this kind of thing. So let's first establish like a base case to work with. Okay. If people say 30, no, never mind. Okay. So what this is going to do, this code, is it's going to generate 30 realizations from a uniform random variable from 0 to 1. We haven't covered this yet. This is just a test case that I'm going to use to demonstrate, and then I'll pick a cutoff value of 0.6. Okay. So then what I'm going to do is, this is the idea here is that these are the two argument names for our function. And right now I'm just working with those specified values in, the script outside of the body so that I can construct the code and verify it as I go. Okay, so count the number of values in X that are greater than C. Okay, so if I look at X, I can do a quick scan and I can see that, yeah, some are greater than C, some aren't. This task could be very, sorry, I should actually specify the full argument. Okay, well, it's going to generate new values. Anyways, I can see some of them are greater than 0.6, some of them aren't. However, I want to, find a way to algorithmically find the correct values. I don't want to be counting these by hand when you can't inside of a function call anyways, because it's going to create the environment and, for the function and, forget about it after the function is called. So, so that we can see that there's some issues here. However, if I were to do, and this is where you would be upset at me if I did this for a quiz, we can do, okay, so prop greater. Okay, so if I do this, then I'm doing a logical comparison, and I'm going to exploit some length coercion again. So I have my vector x of values, and I have my cutoff here. This is going to do the comparison element-wise, and it's going to evaluate whether or not that this statement holds. So now I have a string, or a logical vector, length the same as x. And if we remember from our lectures, as soon as I start doing math to this, it converts these logical values to 0 or 1. Oops, wait a minute. Yeah, okay. So if I have x greater than c here, then this will, should successfully count the number of trues. All right, let me try a slightly smaller example just to verify. Okay, so greater than 0.6. 1, 2, 3 trues, right? Okay, so 1, 2, 3, looks like they're in the same spots. Okay, and then I should get 3, all right? And since I have what's gonna be zeros and ones, I have 3 of them. This is where to get the proportion of values, I could, do something like this. Actually, sorry, length x, but this is actually where the mean function comes in handy. So if I'm going to take these logical values and convert them into 1 zeros, naturally I can just get that proportion directly. Okay, so this should, achieve my task here. Okay, so let's see here. I want this to be a named vector with count and elements. Okay, so let's call this, I don't want to be calling these things, I don't want to make my comparisons and call it twice. If this would be a very large vector, that would be slow. I don't want to repeat myself, so I'm going to give this an intermediary name when I put it in the body of the function. We'll call it comp for comparison. And I want to create a named vector. Let's count. Oh wait, no, sum comp. Okay. And then this is going to be prop. Mean comp, and R is complaining. RStudio is complaining because I need to close this out. Okay. Great. Let's try it out. What am I doing? I could have just referenced it from the global environment and started typing. That would have been faster. Okay. X equals, let's try something that we absolutely know. Okay. 3 numbers and 3 integers from 1 to 10 that are greater than 7. Makes sense. Okay, same sort of thing. Okay, looks good. And let's just for fun do something like our unit of n equals 1e for 10,000 values, 0.7. Cool. All right. Awesome. The number of values in x that are greater than c. Yeah, technically this count is right. If you don't like that this has these point zeros, you could, make this as dot integer, but we don't need to do that. Okay. All right. So then what are the next tasks? So I'm going to just assume that you've read this. And basically these are going to be the very, very, very similar functions. Okay. So we'll copy it. Greater, less, equal. Okay, so less is simple. Just going to change the sign, and then equal, also simple, but it's a little bit tricky because this won't work. This is assignment. This checks whether or not something is equal, which is we'll get into very, very, very soon. Okay, so let's run all these. Now count prop less, x equals 110, c equals 7, count prop equal, same values of the arguments. Okay, looks good. Okay, so that's good. Let's save it. Add our, why did I close that? It's fine. Go to lab 2. This is counts, right? Okay. Drag it. And save and grade. All right, graded. Okay, good. I got everything right. Awesome. A lot of test cases here. Okay, but that's good. Okay, so I can go right back to assessment overview. Okay, chlorine series. All right, fun. We're gonna be doing some Taylor or variants of or special case of the Taylor series. You can read if you need a little refresher on Taylor series, McLaurin series. There's links here. So okay, first of all, what I need to do is get organized. Control N. I'm gonna clear my global environment. Awesome. And then what do I want to do? I want a function, to save this as series into lab 2. Great. And then I'm going to create a function geom series. And it's going to take 2 arguments, a numeric vector of length 1 and an integer vector of length 1, both these quantities being referenced in the text below. Okay, so the body of my function, I should create a vector that stores elements of a geometric series up to the degree n+1 terms. Okay, so recall that these things converge for absolute value of x, or x in magnitude less than 1. Your function will only be tested for values that converge. Great, awesome. Okay, so this is the geometric, or this is the series we're going to be working with. Okay, so we need our function to return a named vector of the following elements, sum of the first n+1 terms. So the idea here is that n specifies there's a 0 exponent in this geometric series, so that we want to take this out to n terms, so that the the main source of confusion here is going to be the difference between n and n plus 1. All right, so sum of the first n plus 1 terms. True, the value that the series converges to, well, it's given. And the last value of the series we stored. Okay, so let's see here. First n plus 1 terms of this. Okay, let's get a value to work with. 0.5. That's going to be very handy. And then we'll do n equals 8. Okay. So I want the first n plus 1 terms. Okay, so that's gonna the last exponent will be n. First one is gonna be 0. So 0 to n x raised to 0n. Okay, that looks pretty good. Okay, so then this could be series and intermediate argument. Okay, so then sum would equal sum series. Okay, true equals, that's given, 1 divided by 1 minus x. I'm not really gonna, okay, we'll run it just to make sure. 1 divided by 1 minus x. 1 minus x is 0.52. Okay, so that checks out. Good. And if we want to be a little bit careful. Okay, and then last will be the last value of the series that we stored. Okay, so let's see here. So series, recall, is all of this, 9 elements. You do this in 2 ways. You could think to do this, so n is given to us, or you could do length series. Since normally I would recommend doing length of something for this, this is kind of default way for getting pulling out the last element of a vector. However, in this case, since n is something that's provided to us, this should be fine. Okay. Unless, okay, it's fine. Okay, so let's just look at it again. Okay, so series, okay, so that looks like, yeah, so that's working. Okay, so yeah, we've tested this out, looks pretty good. All right, so let's put this into the body of the function. Okay, and what does this need to do? Returns a named vector. Okay, we've already pulled the, oh, I didn't pull the last one. Okay, last equals series. Okay, I think R is gonna complain. It ran out of space. So when you run out of space, you can do a few things. You can just let it go. Oh, I guess I didn't run out of space, but it's a little bit clobbered. You could do something like this if you like. Doesn't really matter. I'm gonna leave it as is. Okay, so let's try our function. All right, geom, okay, no, better practice. Geom series, x equals 0.4, n equals 8. Let's see how it looks. Okay, so you can see that sum and true are very close to each other when, you know, the value gets a little bit closer to 0. And of course, when you up this to 20, it's going to be, actually, let's up it higher, 50. Okay, so now R can't tell the difference. We're like beyond machine precision. Remember dot machine. Actually, so this is the smallest detectable difference between numbers. So we can see that in this case, the last value is already, you know, below essentially machine precision. Okay, so we are, you know, here it's yeah, it's getting Very, very, very small, very, very close. Okay. Let's just see what happens if I do this. Oh, wow. Still very far away. Yeah, well, I guess that makes sense. Okay. All right, looks good. Let's go on. So now we want to write a function exp series. And it looks like I have some true last, x and n. So this is going to be very, very similar. Okay. So I want some true and n. So what's going to change is what's going to go right here. So I still need to do something. You know what? R will complain here probably. I guess it's not. Okay. Anyway, so this is my new formula. I have the same idea as series. Darn, I shouldn't have gotten rid of that. I'm going to need the same terms. However, I need to divide by, oops, I should. Okay, so you can see I'm getting a little bit sloppy, a little bit careless. And I'm having to go back and do things. If I would have just kept series and then edited this out, it would fail the cases when I uploaded it. So maybe I was going a little bit too fast, but you can see now why it's good practice to operate outside of the body of a function. In fact, let's just get rid of it. Okay. X0 to n, you can see that's 1, x squared, x cubed, so forth and so on. So I do need the same part. Okay, so what happens if I do factorial 1 through or 0 through? Okay. So there's a factorial function. I think we briefly covered it when we talked about special functions. Was it special? Yeah. Or, well, we highlighted special functions, and that was one of them. So, yeah, it's something that would have been kind of a deep cut, but presumably you can go to Google and type in how to do factorials in R, and then that would give you the answer for this. So essentially what I'm doing is I'm using this function, factorial, and I can supply a vector of type integer into it, and it will evaluate that vector element-wise, giving me the quantities I need. Okay, so I need to do, and I can see that the first one is 1, second one is 1, and when I have this, I have 1, 0.5. See, x is still saved in my global environment. The function call, which took on arguments x, even though I tested it for different values, didn't change x in the global environment. So I still have the x 0.5, something, make sure that we keep track of what's going on in the global environment as we're working. Okay, so anyways, I have x raised to this power, 1, 0.5, and then I can see how, with these factorials, how this is gonna produce the first n plus 1 terms of this quite nicely. Okay, does that just, let's be a little more organized. Don't think I need parentheses there. Okay, so now this is what we called series last time. Okay, now true equals, it's given to us, right? Okay, and then last equals series n plus 1. All right, so we sort of tested it already, but let's look at it again. Okay, series true. Oh, I'm forgetting, man, I am going a little bit too fast here. That's right, some series. Okay, so yeah, looks pretty close. Okay, good. All right, awesome. Let's put in the code. And of course, this is going to be a named vector of outputs. Okay, we're in business. All right, X series, X equals, let's try 1, N equals 20. Okay. Yeah, looks good. N equals 5. Now we can see that the sum is a little bit further away. X equals 3. Now you can see that sum is decently far away from true. But if we ramp it up, we are very, very close. Cool. All right, so I think, is there anything else? Nope, that's it. Okay, let's save it. And go upload series. Save and grade. Pass my test cases. Awesome. All right, so that is the second lab. Yeah, so I would, what was I gonna say? So I know that I'm going through doing these lab assignments, and I appreciate you following along with it. I think that it is very helpful. It will be very helpful for you to try to type the code up as we're going through, like actually just like physically doing, like trying to like, code it, not just like directly copy the answers that I'm giving. I know that I'm giving the answers, of course, but the more practice that you can get with programming, the better. So this is sort of, kind of a safe environment to get some points, but it's also a safe environment to just like practice, and it doesn't really matter. You get unlimited attempts, and you have me right here to give the answers as a checker before you upload. So I would take that opportunity to actually do some additional programming and get some practice. But anyways, here's the video. Thank you for watching, and I will of course see you next week. All right, take care and bye.